Hello and welcome to the discussion about our own galaxy, the Milky Way galaxy. We will be talking about the Milky Way galaxy as our home. We'll analyze different parts of the galaxy and also talk a little bit about the history behind what we know, different models that have evolved over the years, how we've viewed the Milky Way as time has gone by. Now, the Milky Way is, of course, our home. It's sort of an island in the much larger universe. We look at the different structures that we know in the world around us. And in our observable universe, we have the Earth and Moon, which are the closest gravitational bound system that we have. Then going to the next size, we have our solar system, where the Earth and the other 7 planets orbit it, along with other minor bodies. But our solar system itself is actually gravitationally bound to a much larger system, and that, of course, is the Milky Way. Now, when you think about our solar system is much, much smaller in size than our galaxy, even if you take the most distant bodies in our solar system. Well beyond the planets. I mean, if you go out to the furthest planet, Neptune, which is 40 times further from the sun than we are, you are probably only talking about a few light minutes. If you go even further out to the Kuiper Belt and the Oort cloud, at most, you're probably talking about a half a light year from the sun, and these bodies which are, that far from our sun, are only weakly gravitationally bound anyway. Our Milky Way is over 100,000 light years across, if we only include the visible matter, that's being the stars, the molecular clouds, and everything else. Its gravitational influence and the dark matter, which comprise most of its mass, extend far beyond that. So in terms of scales, the Milky Way is much, much larger than our solar system. Probably about 6 orders of magnitude greater, if you want to include the gravitational domain of our solar system compared to the gravitational domain of the Milky Way. Now, the Milky Way itself includes about 100 billion stars. At least we know there are about 100 billion stars. That would be a conservative estimate. The most liberal estimates probably take it out to about 50 billion stars. And the entire mass of the Milky Way, however, is probably just a little under 1 trillion times the mass of our sun, 700 billion times more massive than our sun. And that's pretty significant when you consider the fact that our sun is really much more massive than the median star out there. Now, it's important to note that if we could move away from the Milky Way, we would probably see something that looks like this. We would see this luminous disk, probably not as bright as what we see in this photograph right here, or this rendering. It's not really a photograph. We would see spiral arms. We'd see a bar in the center. It'd be, of course, most luminous toward the very center. But it'd be sort of this flat disk. Really, most of the matter, most of the source of gravity for the Milky Way is actually contained in an exotic form of matter that you can't even see. And it's very appropriately called dark matter because not only doesn't it seem to interact like normal matter would, okay, because of its very weak interaction, it doesn't even interact with light. So, it's not visible to the naked eye. The only way that we know that it's there is because of its gravitational influence. It adds weight to the Milky Way, it makes it more massive, and therefore it affects the way stars orbit, so we do know it's there. So once again, Milky Way It's our home. It is the gravitationally bound collection of stars and other matters, other forms of matter, which our sun, our solar system, orbit within. And we are actually inside this flat disk-like structure. Now, for us, it's pretty much like being in the middle of a forest. Okay? If you could go up in a hot air balloon or you could go up in a plane and look at the forest from above, you could see the structure of the forest. You could understand how far the forest extended, where it began, where it ended, where the elevation was greater, where the trees were denser. But if you are walking inside the forest, you only know about the local location of the forest. You only know about what trees are near you. The trees block your view from seeing more distant parts of the forest, other trees, and other structures that might be in the forest. And we're sort of in the same thing with our Milky Way. We're inside the Milky Way. So when we're looking at the nighttime sky, we can see this luminous band in the nighttime sky, which, of course, is not lined up with the ecliptic, so it or even the Earth's rotation. So it sort of comes up at an angle. But basically what we're seeing, this luminous glow, is not really the entire galaxy, but only the stars closest to us, which are not blocked by clouds of gas and dust. So you look up at the nighttime sky and you see, first of all, bright points of light. These are the stars that are very close to us. The stars that are more distant and not close enough to see as individual points produce this glow. But in fact, the actual Milky Way itself, 95% of the Milky Way, probably even more than that, extend far beyond what we can see, and again are blocked by clouds of gas and dust. So seeing the forest for the trees, so to speak, seeing the structure of the Milky Way has always been a great challenge for us and still remains a considerable challenge for us. It's one of the reasons why we took so long to actually realize that we were inside this massive structure we call the Milky Way. Of course, the Milky Way gets its name because this band of light was originally called the Milky Way. And now, of course, we've given that same name to the galaxy that extends beyond this faint band of light that we can see. So let's take a look at the historical background of the Milky Way. The Milky Way has always been the way it is, at least over the time that humans have been around. But our view of what the Milky Way has really changed. Now, it all starts with Galileo because, as you know, Galileo was really the first to point a telescope up into the nighttime sky and really make nice observations. And even in Galileo's first crude telescope, the Milky Way, this band of light, did resolve into individual stars. So Galileo was aware that this band of light, this nebulous glow, actually was composed of fainter, smaller stars that were not visible with the naked eye, but were visible with his telescope. Now, Galileo never really took it any further than that. Again, his telescope really wasn't powerful enough to see much beyond that. This glow was, composed of stars, but he was able to influence later thinkers. And one of the interesting models that came up was by Thomas Wright, who actually misinterpreted some of Galileo's observations. And full disclosure, Wright was more interested in creating sort of a religious, a model based more in religion than actually based in empirical evidence. So, Wright was, sort of using some of Galileo's observations, but combining it with some of his interpretations of the Bible. And, Of course, Galileo did observe that this faint band of light was composed of stars, and Wright thought that this thin band would be exactly what you'd expect if you were in this thin hollow sphere of stars. And I really don't know the origin or the bridge going from what was in the Bible and what Wright came up with, but this is one of the earliest models of the Milky Way, which sort of merged religious beliefs with empirical evidence from the scientific world. Of course, Immanuel Kant, who lived in the 1700s, he was actually responsible for some of the initial models that we had of the solar system. Fantastic German philosopher, brilliant mind, and he took Wright's model, but created a different model, sort of misinterpreted what even Wright had done. And what he did is he sort of placed the sun at the center of this thin disk rather than a shell. And this model was further expanded upon by further observations by William Herschel with a very powerful telescope, and tried to confirm what Kant had said, and said that yes, in fact, with his measurements, he could in fact confirm that the sun was embedded in this thin disk. Herschel did make a survey of the sky. He counted about 683 fields of stars, and he simply did sort of a numerical analysis, and he determined the density of the stars of the observable universe. But a big problem that he had is he assumed that all the stars were equal brightness. So if a star was dim, he assumed that it was very far away. And now we know today that stars can be millions of times, if not billions of times, different in luminosity. So this was not very accurate. But it was a better model than what existed before then. And of course, this is Herschel's telescope. His telescope was a great improvement over Galileo's. Instead of a small telescope which had a lens that was perhaps a couple inches in diameter, Herschel used a massive telescope which was 4 feet across. The mirror was based on Newton's idea of a reflector telescope. And of course, between the model which Kant had come up with and Herschel's model, we sort of had this rough grindstone model, if you will. Basically, you can imagine sort of a frisbee type structure where the sun was at the center. Now, the next improvement of this model was made by Jacobus Kapteyn, and he was one of the first astronomers to realize that the motion of the stars near the sun were not random. They were actually grouped into separately moving streams. Some were moving, in one direction, some were moving in another direction. Now we know today that stars closer to the center of the galaxy move faster. Stars further from the center of the galaxy move slower. So these opposite streams were really those stars orbiting closer to the center and those stars orbiting further from the center. And we call this proper motion. And Kapteyn used this proper motion to come up with a improved model of our galaxy. His new model didn't place the sun at the center, so it wasn't a solar-centric, if you will, model of our galaxy. It sort of placed it off-center. But the problem with Kapteyn's measurements is he was measuring stars within the plane of our galaxy. And the problem is you can only see so far. So he came up with a grossly, well, not a grossly, a somewhat small model for our galaxy, and he placed the sun far too close to the center. But at least the model of our galaxy was improving. Finally, we really owe our modern view of the Milky Way to Harlow Shapley. He was able to actually measure periodic variable stars, and these are very nice stars for finding distances. Periodic stars have a luminosity that goes up and down with the period, which is directly related to their size. So what he would do is he'd try to look for these periodic stars in different parts of the sky. He would then use the period to estimate how bright the star should be, and then the actual brightness that they would appear in the sky. He would use those two measurements to find their distance. And the periodic stars that he used were R Lyrae stars. And he, instead of concentrating on the disk, which again was really where Kapteyn ran into problems, he concentrated on the halo, the region above and below the disk of the galaxy to measure distances. And in particular, he concentrated on a type of cluster of stars that we'll talk about later on called globular clusters. And from this, he was able to come up with a fairly accurate model for our galaxy, which really hasn't changed very much. I guess beyond what Shapley had done, the major changes that we've made is we now realize that it's not just an even disk of stars, but in fact our galaxy is a spiral galaxy in that it has these spiral arms. So let's start talking about different populations of stars in our galaxy. Okay, our galaxy actually has different regions where we have stars of different ages. The interesting thing is that when our galaxy formed, you had stars that formed almost instantly with the galaxy itself. And then you have more recent stars that are constantly forming within the disk of the galaxy. So we have these two different populations of stars, those that are scattered all over the place that have been around for a very long time. We're going to call these population 2 stars. And those stars like our sun, which formed much later after our galaxy had already established itself. So the whole idea of these populations of stars has to do, or originally, the grouping of these populations has to do with their spectra. Now, when the universe formed, general theory has that there are basically only two elements that formed, hydrogen and helium. Yes, a little bit of lithium formed too, but for the most part, almost all the available material to build stars was hydrogen and helium. We know from earlier discussions that stars tend to take lighter elements like hydrogen and helium and process them and turn them into heavier elements. Now, when very massive stars die, they blow this material into space where it just basically spreads out and mixes in with the hydrogen and helium. So as time goes by, stars that form tend to have more of these heavier elements. So again, stars are mostly hydrogen and helium with small traces of heavy elements. You can actually get a sense of when a star formed based on how much of these heavy elements they have. We call these metals, even though they may not be chemical metals. They were basically given this name long ago. Metal just means anything heavier than helium. We talk about the concentration of these trace elements in terms of metallicity. Again, when our universe was first formed, the metallicity of the matter was basically zero. As stars were born and died, more and more metals accumulated. So the stars that are forming today, what we call population 1 stars, kind of strange because you'd think that, the first stars that formed would be pop 1 stars, and then the next population would be population 2, so on and so forth. But it actually works backwards. Population 1 stars are the most recent stars. They are the generation of now. They're stars that are forming today. So our sun and most stars younger than 10 billion years old are classified as population 1 stars because, believe it or not, even though our universe is only about 13.7 billion years, by the time 10 billion years ago happened, when the universe is about 4 billion years old, most of the star formation had already happened. Okay? The rate of star formation has really decreased since. So the metals had plenty of time in the first 4 billion years to build up. So again, these stars come in all different masses. Some are very small. About the biggest you're going to get from population 1 stars is probably somewhere up around 60 times the mass of our sun. But again, these population 1 stars are, rich in these heavier materials because they came after the stars that produced them. Another interesting thing about the population 1 stars. Now, look at this diagram right here. This is sort of like an overhead shot of what our Milky Way might look like if we included only the population 1 stars. And what we're seeing here are circles which represent the orbits. Population 1 stars are in this rotating disk, so they tend to have these very regular orbits. They tend to stay within the disk. The disk is only a few light years, in thickness, and like the planets in our solar system, they tend to orbit in a very orderly fashion around the center of our galaxy. Now, population 2 stars, these are the older stars. Many, again, formed very early on during the beginning of our galaxy. And they generally, when you come across population 2 stars, they're generally small. And this makes sense because any massive population 2 star, if these are old stars, would have gone supernova a long time ago, or would have died a long time ago. They would have exhausted their fuel. Even our sun, if you think about it, if our sun formed during the first billion years of our universe, it would be pretty much at the end of its giant phase. It probably would have already gone on to become a planetary nebula. So population 2 stars, these are old timers, okay? And only low mass stars can survive that long. We tend to find the population 2 stars all over the place. Their spectra are very weak in terms of the metal lines, and they tend to be orbiting in these elliptical orbits, which are scattered all over the place. They're not really in the disk of the galaxy. Again, they're generally old, and they're basically the second generation of stars that formed in our galaxy. So, if you're sort of to map out our galaxy, and you're looking at our galaxy edge on, those stars that are the newest, what we might call extreme population 1 stars, would be right in the edge of the disk, right edge on in the disk. As these stars age, they tend to be gravitationally perturbed. They might start moving out of the disk. As you get further out of the disk, then you tend to get more of a mixture of population 1 and 2 stars. Further away from that, more population 2 stars. And then finally, in the halo of our galaxy, which is sort of the spherical region that surrounds this disk, then you'd have just a lot of old stars. Now, there is such a thing as population 3. These stars, we basically say, are pretty much extinct. There have been some exceptions, we think, where some stars might have formed from pristine hydrogen and helium recently. That's not been affected, but by the existence of other stars. But for the most part, population 3 stars are an ancient type of star that formed very early on in the universe, within the first billion years. And the interesting thing is they would have been very massive, for the most part, because hydrogen and helium, um, aren't supported as well by light. Stars basically have gravity trying to push them in, then you have heat and light pushing them out. They're very transparent, so they could grow to much larger sizes than the stars that we have today. The upper limit for stars forming today, might be around 100 times the mass of the sun. And these types of stars would be very low in terms of their metals. Population 3 stars, for the most part, could have even started with a lower mass limit, around 100 times the mass of the sun, and gone all the way up to 1,000 times the mass of the sun if they were made out of pure hydrogen and helium. But again, these stars are not really thought to exist today. Maybe there's an exception, an exception to the exception to the exception. But these stars were really responsible for creating the first elements heavier than helium and our existence. Think about the Earth. The Earth is made mostly out of silicon and oxygen, two elements that had to be synthesized in heavy stars. So those are the two populations of stars that we have today. Again, the disk of our galaxy, where most of the stars are concentrated, that's where you'll find the youngest stars, because that's where the molecular clouds are. That's where new stars are being formed all the time. The older, less luminous stars tend to be scattered all over the place. Now, stars generally don't form as individuals. Stars generally form as huge clusters, okay? And there are two basic clusters that stars come in. The first type is where we see a lot of the population 1 stars. We call these open clusters, as opposed to globular clusters that we'll talk about later on. Again, these are young groups of stars. Our sun probably formed in an open cluster. As time goes by, these open clusters tend to fall apart, and the stars go on their own way, much like our own sun has done. So, again, two basic categories: the open clusters, which we'll talk about right now, and the globular clusters that we'll talk about in a little bit. Okay? Again, we generally see these clusters forming in groups of somewhere between 100 and 1,000 stars. Is probably fairly common, and in terms of the size of these clusters, they're somewhere between 10 and 60 light years across. Now, this is one of the most famous open clusters. You can actually see this with the naked eye. This is the Pleiades. If you're Japanese, you'd call it Subaru. And yes, the car Subaru was actually named after this. This is in the constellation Taurus. And the Pleiades are a very beautiful open cluster. The luminosity, the nebula that you see around it, is actually not associated with the formation of the stars, but rather just a cloud of gas that the stars are passing through. Other examples of open clusters include the jewel box cluster, not quite as famous as the Pleiades, the beehive cluster, and the Hyades, which are actually very close to the Pleiades. This red star, or orangish red star, is actually Antares, and that is the eye of Taurus the bull. Here's another view of the jewel box cluster. It's a very young open cluster. It's not visible from the northern hemisphere. It's actually in the constellation Crux, the Southern Cross. And because it's very young, it actually has some very, very massive stars in it. And in most open clusters, the stars are too old for these first massive stars to form. So, jewel box cluster is a very interesting cluster, a very young cluster that we can see what our own solar system might have been a member of very early on. If you want to get really young, we can go inside an actual molecular cloud. And this sort of shows the transition from star-forming region to open cluster. And this cluster right here is called the trapezium. It is what lights up the Great Orion Nebula. And what is happening now is these clusters of stars, this cluster of stars, is actually dispersing all the gas and dust from which it formed from. So star clusters actually destroy the nursery from which they came from. Here's another very young open cluster, also embedded in a giant molecular cloud. And here you can see this cluster right here. And again, it's beginning to dissipate its surroundings. The wind from the stars is actually carving out a hollow space, and soon the nebula will be gone, and this cluster of stars will be off on its own. And this is looking even closer inside it. The Tarantula Nebula, in fact, is actually home to many forming open clusters, and one of the clusters, it contains some of the most massive stars that we know of in the universe. The cluster is called R136, and the most massive star known to exist is known as R136A1. And the A basically corresponds to a region that they thought was originally a single star, and number 1 is the brightest of these central stars. So again, this is where the open clusters come from. Now, the two closest open clusters to us probably formed from the same molecular cloud. In the top image, we have the Hyades, which again, this bright star right here is, did I call it Antares? Antares is the brightest star in Scorpius. I apologize. It's Aldebaran. And Aldebaran is a red giant, and that's why it's so bright. And in the lower picture, we have another cluster, the Beehive cluster in Cancer. Now, again, these are older clusters, so the stars are more spread apart. This cluster is beginning to come apart. And the interesting thing is that as these clusters evolve, we can actually tell how the populations change as a function of time. Now, again, open clusters are an excellent laboratory for stellar evolution because they basically have the most massive stars end their lives much earlier than the lower mass stars. So basically, you can find out when the cluster formed because, very simply, the fewer massive stars that it has, or where the massive stars actually cut off, pretty much determines, how old the cluster is. Sorry for that pause. So let's take a look at our HR diagram. The HR diagram basically plots luminosity as a function of temperature. And we see two clusters here. Now, in the upper left-hand corner, we generally see stars that are more massive and stars that are hotter. Okay? So our hottest and most massive stars are going to be in the main sequence up here. Now, the coolest stars that live the longest, the red dwarfs, are down here. Notice we're taking a look at two clusters right here. The first one is NGC 188, okay? And you notice that with that particular cluster, that it starts moving away from the main sequence right about along this line. Okay? Now the second cluster, M67, actually has some more stars on the main sequence. It goes about this far. Okay? So, what can we conclude? Well, once again, NGC 188 is older because the most massive stars that it has on the main sequence stop about right there. M67 is a little bit older because it has a few more massive stars still left on the main sequence. And here's a real nice composite showing how a cluster would evolve over time. Here's what we'd expect for a cluster of stars that had just formed. Now you can see that in the next picture, the most massive stars are going through their supergiant phase. Then in 3, we can see that now middleweight stars are beginning to go through their giant phase. And then finally, even sun-sized stars are going away. Now even stars that are less massive than our sun have evolved already. And again, you look at the first picture, and we're looking at stars that are perhaps, or a cluster that's perhaps just formed. Okay? Now if we look at slide 4, we know that the sun, probably has a lifespan of about 10 billion years. That's where their turnoff point is, right about where the sun is. So cluster 4 would have formed about 10 billion years ago. And again, you can see more of that in this diagram right here. Okay? Very young clusters of stars. NGC 2362 just formed, so it has almost all of its stars in the main sequence. The Pleiades a little bit further down. Okay? Turn-off point's a little bit further down. And then here's a very old cluster, M67. Now, again, open clusters don't live forever. Okay? You don't have these stars that form together and then die together. Basically, what happens over time is the cluster may initially form a very tight grouping. Nice gravitational pull on each star. The whole cluster orbits around the center of the galaxy. As time goes by, however, tidal forces begin to break some of the member stars apart. The cluster star is elongated, and eventually, as a cluster loses more and more stars, it loses more of its gravitational binding forces, and therefore, eventually, there are no stars left. Our sun, whatever cluster it was part of, dispersed a long time ago. We were probably not a member of a very large cluster, or we were one of the first stars to get ripped apart, but we can't find any of the stars that the sun formed with. So those are the open clusters. Again, they are all population 1 stars. They all formed within the disk of our galaxy. New clusters are coming and going all the time. Globular clusters are something that are quite different. Globular clusters are much older. Now, we don't understand globular clusters as well as we do with the open clusters. With the globular clusters, the original idea was we thought they all formed at the same time as a galaxy. Now we're starting to see some of them may have formed a little bit later. But the globular clusters were really the clusters of stars that were studied by Shapley, and the stars that he used to determine the structure of the Milky Way. Again, clusters are much larger than open clusters. Here, instead of 100 to 1,000 stars, we actually have 100,000 to 1,000,000 stars. And, that makes them, 3 orders of magnitude larger. than our open clusters. Again, the globular clusters are, population 2 stars, very old stars. Some models had them forming with the Milky Way or with whatever parent galaxy they're with, as just very large star clusters. Other models seem to indicate that the globular clusters may have been just small galaxies captured by the parent galaxy. The general consensus is we don't know. There's certainly some globular clusters that seem to favor formation with the galaxy. Others really look like they're dwarf galaxies that were captured. So both models could actually be correct. A really big, the largest of all the globular clusters, was by the name of Omega Centauri. And Omega Centauri was originally thought to just be a single star. It's the brightest and largest globular cluster in the Milky Way. It's about 86 light years across and has about 1 million stars. So, it's about the upper end of what we see with globular clusters. And again, there's good evidence that this was not a cluster that formed with our galaxy, but may have been a former galaxy which basically had its outer regions ripped away, and all that was left was the center. And this is the globular cluster that we see today. And here's a close-up of this. Really, this is taken with the Hubble Space Telescope, so we get a really nice close-up of this. And what we see inside this cluster is a lot of old stars. Some have become giant. The brighter stars are the giant stars. And there's some interesting stars in here, which are blue in color, that they call blue stragglers. These are stars that are thought to be 2 small stars or 2 or more small stars that merge together to make a more massive star that should have died out long ago. Here's another globular cluster. This M15 is in the constellation Perseus. And again, you can see there is a very high density of stars toward the center. And then as you get further and further away, the density drops off. And again, globular clusters, like all population 2 stars, tend to orbit in very elliptical, random orbits outside the disk of the galaxy. Now, once again, how are we able to develop the picture of the Milky Way that we have today? Well, let's start out by, first of all, saying what we know about our galaxy today. Again, the current structure basically has the very center of our galaxy, known as the nucleus, occupied by a very dense region. We now know that the nucleus actually contains a supermassive black hole, and we'll talk about that more. Surrounding the nucleus is a less dense, but much denser than the rest of the galaxy, this nuclear bulge, which sort of is a thickening of the disk, if you will. The disk where we live in, and globular clusters, which are out in the halo of our Milky Way. And again, this view has been developed using many years of study. Now, originally, before we had great satellites like Hipparchus, you couldn't use parallax observations to measure the distance of stars. You had to do what Shapley did. You had to rely on these variable stars to figure out where different stars were located, to measure distances. And again, variable stars are any stars that change their luminosity with time,
But the important ones are the periodic variable stars, those that have a repeating pattern where they go bright and dark and bright and dark. And again, Shapley used these variable stars to figure out where different parts of our galaxy were located, how far away were they. Now, again, originally he concentrated mainly on the globular clusters to get an overall size of the Milky Way. Later on, other information was obtained, such as the spiral arms of our galaxy using radio telescopes. Again, just a little background on variable stars. If you look at the HR diagram, there's a green strip that cuts across the HR diagram called the instability strip. Stars that are not on the main sequence, so they're a little less stable than most, which are along this instability strip, tend to be variable stars, tend to be periodic. Now the problem is it's got to be a giant or a supergiant star in order to stimulate these instabilities. So right along this green line here is where we find these variable stars. So main sequence stars aren't great for finding great distances. It's really your giant stars on this instability strip and supergiant stars that are going to help you judge distances. Now, the source of the instability is thought to be actually almost like a spring. And again, got to emphasize here, not all stars on the strip are variable or periodic. But they're, especially in these giant stars, there's a region of ionized gas that basically acts like a spring. And that if you get the spring to start vibrating, you'll drive these oscillations, and these oscillations become periodic. Again, main sequence stars don't have it, but even some white dwarfs and giants have the proper structure to create this. Now, there are different types of these periodic stars, and they're named after prototype stars where this behavior was first seen. The first type of periodic stars are the Cephid variables, named after a star in the constellation Cephus. We've actually broken this down into two types. The first type is called type 1 Cephids. They're the most massive and largest of the pulsating stars. They are large giants, and in some cases even supergiants. And because they're so large, they're the ones with the longest periods. Other good periodic stars to use to measure distances are type 2 Cephids. They're giants, not quite as large as the type 1 stars, and their periods are a little bit shorter, anywhere from 33 to 30 days. They're more practical stars to use because measuring periods over 100 days takes a lot of data points and a lot of observations. Finally, the stars that were used by Shapley were the R Lyrae stars. These are subgiants which have periods somewhere between 2/10 of a day, okay, and 1 full day. So, anywhere from about 5 hours to 24 hours. And again, if you want to see these on the HR diagram, here again are your type 1 Cephid variables, your giant and your supergiant stars on the instability strip. They're your type 2, down in the giant region. Again, you notice that the bigger they are, the longer the period. And then the R Lyrae stars, which are subgiants, down here. Now, going back to what Shapley did, again, he didn't get the entire picture, but he got most of the picture. He basically looked at the globular clusters that could be seen from Earth, and they're above and below the disk, so they're not blocked by other stars or molecular clouds. And he noticed that the largest concentration of these globular clusters was in the direction of Sagittarius. There are more on one side of the sky than there are on the other side of the sky. So what this seemed to indicate is that if we were in the center of our galaxy, then we would expect to see an equal distribution. It's not what we saw. The further we are from the center, the more we should see toward the center of our galaxy, where there should be fewer globular clusters away from the center. And again, you can see this in this diagram right here. Notice that, again, if you sort of cut the sky in half and our sun is located in the disk, you would see many more globular clusters on this side and much fewer on the other side. And that helped Shapley develop his model of our galaxy. Now again, this is showing the basic structure of our galaxy. The nucleus is at the center. The nuclear bulge sort of sticks out like the yolk of a sunny side egg. And the disk is sort of like the white part. That's the part that we're in. And then again, the halo extends much beyond that. Now, if you look at the sky and you're mapping the sky and you look at the Milky Way, all you see is this band of light. Okay? It's really hard to discern structure from this. This is because that light band that you see is really the stars that are closest to us. Any stars that are further away are going to be blocked by all the gas and dust, which is concentrated in the disk of our galaxy. These molecular clouds don't let light through. In fact, if you look at this band of light, you can see some bright parts where you have stars, and you see some dark parts where the molecular clouds are concentrated. Now, with the recent advent of satellites, we're able to see much further through this gas and dust than we were in the past. And the reason for this is, while gas and dust will absorb and scatter visible light, it does much less with infrared light. Now look at the same view of our galaxy, but this time in the infrared part. Looks very similar to the structure that we saw before. We can look through the gas and dust, and what we see instead, we do see how thin the disk is, but we can see that nuclear bulge at the center. And again, we're looking from our perspective. We are within the disk, so we can't quite see this overhead view of the Milky Way. But we have been able to create this reconstruction by not only using the information that we have from the periodic stars, but also by using radio telescopes to basically map the molecular clouds. By identifying where these clouds are located, where they're concentrated, we can actually study their red shifts, the Doppler shifts in the radio signals, and from that determine how the cloud is moving. And then you can discern how far away it is. Let's take a little trip through the Milky Way. We'll start with the closest stars to the sun, and we'll move out. Now we're starting from our location. The sun's at the center. We see the closest stars to us, Proxima Centauri, Alpha Centauri. We see some other important stars, Epsilon Eridani. You see Procyon here. But most of the stars around us are just these red dwarfs. As we go further out, 20 light years away, we see more and more stars. see if I can find some interesting ones. Here's Eta Carina. Oh no, that's not. I'm sorry, that's Eta Cassiopeia. Here's Procyon again. Tau Ceti. Let's go out 200 light years. We still don't see very much structure to the stars. They seem to be completely scattered in all random directions. However, by the time we get out to about 3,000 light years, we start seeing that, in fact, there are places where the stars are concentrated, and these are the actual arms of our galaxy. Here's one arm, and unfortunately this line can't curve. That's the Orion arm. Here's the Pegasus arm. Here's the Sagittarius arm. Go even further out, again, looking at the disk of our galaxy, we can see our location right there, sort of halfway between the center and the edge of the disk. And then you can even see a dwarf galaxy, which is currently being absorbed by our own galaxy. So that's the disk. We're in it. All the stars you see in the sky are in it. Really, the only stars that we don't see in the disk that are visible from the naked eye are maybe in globular clusters. Now, the halo is probably the largest region of our galaxy, but it's also the region with very few stars. In fact, most stars out there are either just stray stars that lost their way or are members of these globular clusters that are just floating around there. Again, the halo extends well beyond the disk of our galaxy, and mostly what's out in the halo is dark matter. We've already talked about the disk of our galaxy. That's where we are. That's where all the population 1 stars are. That's where new stars are forming all the time. As you get closer to the center of our galaxy, we see the nuclear bulge, and for our galaxy is a barred spiral. The nuclear bulge is actually elongated. It's actually stretched out. And again, this has a real mixture of stars, population 1 and population 2 stars. You can barely see this nuclear bulge in this photograph right here. It's looking towards Sagittarius. But again, if you look at the nucleus in the infrared, you can see through a lot of these clouds of gas and dust. Now, at the center of this bulge is the nucleus. Again, radio telescopes and infrared telescopes and X-ray telescopes have allowed us to see much further than we've ever been able to see before. And finally, we can see some of the hidden structure of the Milky Way's nucleus. And the first thing we notice is there are a lot of stars there. If we look in the radio part of the spectrum, what we also see is there's a lot of magnetic activity too. These filaments right here are actually plasma, which has been trapped by our galaxy's magnetic field. At the very center is the location of the black hole. And this black hole's name is called Sagittarius A star. Now, Sagittarius A actually talks about a large cloud of gas and plasma, which is located at the very center of our galaxy. Sagittarius A star is a bright speck within this, and that's where we believe is located a supermassive black hole. Now, here's a weird thing about black holes. We think that black holes and galaxies go hand in hand. Almost all the large galaxies that we see out there have black holes at the center. Even very small galaxies are suspected to have perhaps at least a medium-sized black hole there. The size of this black hole is extremely massive. It's thought to be millions of times more massive than our own sun. Still much less massive than the entire galaxy, but perhaps just like our solar system formed with the star at the center, okay? Our sun is the star at the center of our solar system. Larger structures like galaxies might form with a compact object in the center. Now, no star could be millions of times more massive than the sun, so instead, a black hole forms. Now, the interesting thing is, when the Milky Way formed, this black hole was probably very active. It's probably consuming large amounts of matter. And our galaxy would have been called a quasar because of the intense radiation and light and energy coming from the center. But as time went by, there's less and less available matter for the black hole to scoop up. The black hole became less brilliant, and the stars in our galaxy became the primary shining component. Okay, summary. Let's summarize it. What can we say about our Milky Way? Well, first of all, we are located inside it. We're located in one of the spiral arms of the Milky Way, again, about halfway between the center of our galaxy and the edge of the disk. Our Milky Way is a spiral galaxy. It's actually a barred spiral galaxy. And it's part of a larger group of galaxies known as the local group that we'll talk about next time. The nuclear bulge contains a high concentration of stars, the highest in the entire galaxy. The disk is the next most concentrated. At the center of the Milky Way, there's a massive black hole, and the halo of the galaxy contains old metal-poor stars and large clusters called globular clusters. Okay. Well, thank you very much, and that concludes our discussion of the Milky Way.